Alright, hey guys. So, this is the first stream I've ever put together, so we'll see how this ends up going. Playing around with OBS and settings and things like that. If the music is too much, let me know, I'll turn it down. And yeah, otherwise I am working on a textbook right now. And I thought I'd just go ahead and start streaming the writing process because honestly I need something to like keep me on target and keep me focused. So I'm working on this book. Is data-driven methods in dynamical systems. This book is something I'm writing together with Rishikesh Kamalapurkar and Benjamin Rosso. I am mostly doing the writing, the initial writing, so so it's on my shoulders right now before I pass the book to them. So I opened this template. It's just a Springer template for writing this book, just because I need something to keep me organized. And so we have a whole bunch of like little extra things we can ignore here, but generally speaking, the idea is that we're trying to put in the mathematics of machine learning, and in particular, I want to talk about the mathematics and the machine learning methods that go into data-driven methods in dynamical systems. So it's going to have a bunch of preliminaries, and that's going to include basic analysis, Fourier Transforms, stuff like that. I'm thinking about putting the Fourier Transform stuff actually in the appendix, but one or the other, and that's what we're going to be talking about today. I'm also going to be talking about Hilbert spaces, so I've been making a whole bunch of videos on my channel for Hilbert spaces, and the idea is that this is ultimately going to connect back into the book. So we'll have QR codes that link from the textbook to these various videos. And so if you want, please don't leave the stream yet, but if you want to check out those videos, I have a whole playlist on the mathematics of machine learning, and it starts with Hilbert spaces because I really think that is the place to start. And then we're going to get into reproducing kernel Hilbert spaces. This is, sort of my jam. It's like everything that I've been doing since I entered graduate school. So reproducing kernel Hilbert spaces, I think, has been in like every single one of my papers since my first publication, with the exception of maybe one or two that were really authored by other people. And so, reproducible kernel Hilbert spaces, I think, play an extremely important role in machine learning. They are very classical, going back to the Paley-Wiener space and Shannon sampling theorem, things like that, and even earlier than that. But as far as like machine learning and data science, I think that's really kind of where they start. But then in the 80s, you have things like people like Vapnik and others introducing them to support vector machines and other things like that. And today we use them for scattered data approximation, and I've used them a lot in the sort of interaction between these sort of operator theoretic methods and etc. Then ultimately we'll get into inverse problems and then operators on Hilbert spaces. This is going to lead into things like Koopmanism and Koopman operators and all that good stuff. And then there's also an intersection between operator theory and regularization methods, and so that'll be fun to talk about when we get there. So then the meat of the book is really going to be in part 2, where we start learning dynamical systems. And so we have basically a system that we've observed move and things like that, and so it's going to get into occupation kernels and regression approaches. We're going to have parameter identification. That's going to be the whole thing in there. It's things like Cindy, weak Cindy, and some of my own methods in there as well. Then we'll have a whole bunch on Koopman operator theory, but this is really going to be Koopman operators more or less from the way that I see them and their role and their interactions between reproducing kernels and dynamics and stuff like that. We will talk about the Koopman semigroup and all that stuff to a certain extent, ergodic theory, just so we make sure we touch all our bases. But that's not really how I approach a lot of these problems, and so it'll be fun to sort of put this my own spin on a lot of these things. Then ultimately it gets into dynamic mode decomposition. Now, part 3 actually kind of intersects a lot of things that we have working right now. And so things that we have either under review or we're writing up and things like that. So operator decompositions and vector value reproduced kernel Hilbert spaces. So this method of doing learning theory is something that I'm actually writing up as a paper, and maybe I'll put that on stream at some point. But that's going to be this chapter, and it's going to connect to a lot of things that we've been doing with Liouville operators and control theory and all that stuff. So anyway, lots of stuff coming. And then after this, I guess I haven't labeled those yet. But yeah, so this is basically a quick like sketch of what I think is going to go into the book, and I think that could be fun. I don't know. Anyway, so happy to have you guys here for those who are watching the stream, and yeah, it'll be fun to go into it. But in order to talk about reproducible kernel Hilbert spaces, we would really need to talk about things like the Gaussian RBF. And if we're going to talk about the Gaussian RBF and Real basis functions in particular, then what we need to do is we need to actually define them, and also to get convergence rates and things like that, we're really going to need to frame them in terms of the Fourier transform. And so I want to talk about the foundations of the Fourier transform today, and sort of sketch that out so we can start getting that into into the appendix of the book, so that could actually make some sense. Anyway, so let's go ahead and start sketching some things out. So let's go ahead and tablet. So I have my whiteboard. I have a camera on my whiteboard right now. I don't really feel like standing, so we'll just do things on my tablet. Anyway, so we're going to be talking about. So here we're going to be talking about the Fourier transform. Oh, that's too thick. So we have the Fourier transform. And with the Fourier transform, there's something in particular that we really need to address, and that is, first of all, we need to talk about the definition. And after the definition, we need to talk about, more or less the conditions that we need, conditions for it to be well defined. And today on stream, we can talk about sort of the continuity of these guys. And so the continuity of Fourier transforms, it comes down to a couple of things. First of all, we have the definition. And then we also have, the dominated convergence theorem. And continuity, this is really just going to work for L1 functions. And so that's something we're going to have to distinguish here. So we have these definitions of the Fourier transform, conditions for it to be well defined, continuity, at least for L1 functions. And I guess I want to talk about one other thing, and that is the Riemann-Lebesgue lemma. And so the Riemann-Lebesgue lemma, right? So the Riemann-Lebesgue lemma basically tells us that for an L1 function, that we're going to decay as we go off to infinity. And I think these four things, hopefully we can accomplish them. At least me laying them out on the tablet here for you guys. We can get that all laid out as sort of maybe a mini lesson while I try to organize my thoughts and before writing it up. And I might make a bunch of mistakes. I have the scattered data approximation book right next to me in case I need to look up something that I forget. So I'm not perfect. These things happen. So we'll see. But both of these are going to have to use the dominated convergence theorem. So that's going to be something we're going to need to address maybe pretty early on. And the Riemann-Lebesgue lemma is sort of kind of interesting how you have to get at the result, because first you have to prove everything works for compactly supported continuous functions, and then sort of complete it underneath some sort of like continuity argument. And but at least for the definition, that's easy to write down. Do I want to do things for? Let's just do things for just basic real numbers. We could do it for Rn, and maybe we'll soup that up later, but we'll keep it simple. So what we're going to have is we're going to have the definition here, and the definition of Fourier transform is basically for a function say f going from R to R, or, well, I guess we can say C. Come back, there, to C, the Fourier transform of F, denoted again, like textbook speak, denoted as, say, we'll just put f hat here at, say, w or omega and r is given as this. So we have f hat of omega is equal to 1 over the square root of 2 pi times the integral from minus infinity, let's just say integral over r, of f of x times e to the minus I xw, or omega dx. Okay, so a few things to say about this definition that we have right here. First of all, we have this coefficient, 1 over square root of 2 pi. If you've seen the Fourier transform before, you might not have seen it like this. And so, in particular, sometimes this is just left off, and then this is given as a Fourier transform. And in those cases, I think that's usually what physicists do. And then later when they do the inverse Fourier transform, they have to catch back up, and they divide by 1 over 2 pi. And then engineers, I've seen a lot of them put in like 2 pi up in here, and that changes how the coefficients seem to work out as well. All of these have exactly the same properties. It's just everything's just sort of shifted by a constant or compressed or stretched or other things like that. So all the things I'm telling you is going to be true no matter what definition you choose. Just keep in mind, there might be a shift of a constant or something like that. The advantage of doing this one, and this is called the symmetric definition. So the symmetric definition of the Fourier transform basically tells us that, we can use the Fourier transform again to invert the Fourier transform. You just apply the Fourier transform with a minus sign in your argument, and that's basically the inverse Fourier transform. You don't have to remember, do I use 1 over 2 pi here? Do I use 1 here, etc. So we can use basically the same definition here in order to get one or the other. Another thing to mention is that we are integrating over r. And so instead of just putting minus infinity infinity, which would technically be the same if you're in the right context, but I just kind of want to emphasize that this is an integral that is usually being thought of in the Lebesgue sense. And that's because we want things like absolute integrability implying integrability, which doesn't always happen for the Riemann integral. So then those are sort of 2 caveats I'm going to do, but for the most part you don't really need to worry about those. If we're working with nice continuous functions that decay quickly enough, if you can use Riemann integration, you can use Lebesgue integration, anything will be fine. And in fact, almost all the examples we're going to work with are going to be with continuous functions and usually rapidly decreasing functions like the Gaussian. Okay, so then the question is, let's go ahead and copy this guy over and move it. There we go. And paste. There we go. Make small. Put it over here. Okay. So then, so I said that this is defined as being the Fourier transform, but the definition only works when it makes sense. So sometimes it might turn out that, that integral just doesn't exist, and then you wouldn't really have a Fourier transform at that point. So what we'd really like is we'd like to work with a function that is not going to be too concerned. We're not going to be too concerned about whether or not the Fourier transform exists in a certain area or not. So what we're going to do is, so if, say, f is inside of L1, say, L1 of R, and this is, by the way, the Lebesgue space, which is defined like this. So basically f is going to map from R to C, and we are going to assume that the integral over R of the absolute value of f of x dx is well defined. So we have something like that. So it's finite. So these are functions that are absolutely integrable, and if you have an absolutely integrable function, then that means you have a Fourier transform at every point. So then f hat at omega exists for all omega in R. Okay, so let's talk about that. So I guess let's go ahead and prove that. The proof is pretty trivial. So essentially what we're going to do is we're going to let omega be in R, and recall with Lebesgue integration, that's absolute integration implies integration, integrable, and integrable. There you go. So absolute integrability. Okay, so we start there, and so that's what we get. So we get so we start with that. So what we really need to show is that the Fourier transform, the integral that gives us a Fourier transform, is absolutely integrable, which means that the original thing is integrable. And so that really follows pretty quick. So we're going to have the integral over R of f of x e to the minus I x w dx. This is less than or equal to the integral over R, just by the triangle inequality, of f of x times e to the minus I x w dw, or dx. There we go. And, well, this absolute value is, you split this up over the product. So f of x times the absolute value of e to the minus I x w. And e to the minus I x w is 1. So that is going to give us that this is equal to the integral over R of f of x in absolute values dx, which we know by definition is less than infinity. So there we go. We have integrability. And thank you for everybody who stayed through that short little proof. So there we go. So at the very least, what we know now is that if we have a function, and I just call this a proposition, that if we have a function f that is an L1, then it is going to be have a Fourier transform for every frequency, which is what we call W. So now we have a class of functions where we know this exists. And so we'd like to work with that class of functions. And not only do we want to work with that class of functions, but what we're going to do ultimately is we want to show that Fourier transforms exist for not just L1 functions, but that they could also exist for L2 functions and even distributions. But we can't get to those yet. That takes a little bit of time. So the Riemann-Lebesgue lemma that we're using is going to help us show that this will send what are called short space functions to short space functions. And then in the L2 case, we actually can close up the short space functions inside of L2 in order to give a sort of a sideways definition of Fourier transforms on L2. So that's going to be something we're going to do over the next couple weeks. And then for the distribution theory, that's going to be some time to get to that. But what's interesting is that the distribution theory itself actually led to a Fields medal. All right, so hey Chris, how does definition link up with this transform being an integral transform? And hey Slava. So yeah, okay, so the definition, when we take it to things like L2 and distributions, those aren't actually integral transforms. We will often write the Fourier transform of these functions, but that's not usually what we mean. So, for instance, when we're talking about the Fourier transform, it's an abusive notation, right? So when we're talking about the Fourier transform of L2, then what we're really saying is that we're going to take an L2 function, and then we define the Fourier transform of that L2 function as a sequence of Fourier transforms on functions where we can do that with the integral. And so it ends up being a limit rather than an actual integral. And for distributions, yeah, basically that gets to be a lot more complicated, but basically the integral itself is defined as a new kind of distribution, and we write distributions as integrals as an abusive notation even when they're not. So this is what you see with like the delta function if you take like differential equations. And so, and it's just because we can basically approximate any sort of distribution with a regular distribution, which is actually defined in terms of integrals. And so that's how those integral ideas sort of link up with these definitions. Hope I answered your question okay. But yeah, so now we have this existence, and so that's really nice. We would like to keep going and do a little bit more than that, and we'd like to move on to other properties like continuity and decay. And so continuity is actually really fast to prove, and it'll give us a nice sort of connection with it'll give us a nice preview of what we need with using cool, I'm glad it helped. It help us make this sort of connection with the dominated convergence theorem. So let's talk about dominated convergence theorem. This is going to be a really light version of dominated convergence theorem. It's not the big one. It's just what we need. So dominated convergence. So really what we're going to want to do is we're going to want to pass a limit through an integral. And this is usually a big no-no unless you have certain conditions. And so dominated convergence gives us a set of conditions that we can use in order to pass a limit through the integration. And in particular, I mean, this is it's a limit through an integral, and this is going to be a Lebesgue integral, which is not really defined in terms of limits of, you know, points and things like that, like you would with like a Riemann integral. So it does. So it's a lot more complicated, and I'm by no means going to prove this on this stream, but essentially this is what we're going to end up having. So what we have is that we have if f m is inside of, say, L1 of R, and fm of x converges to f of x for all x in R, so we get pointwise convergence. And there exists some sort of g of x, say g in L1 of R, then such that we get fm of x is bounded by g of x, absolute value for all x. All right, yeah, there we go. Then we have the integral of fm of x dx converges to the integral of f of x dx. And I think we need this guy we say is immeasurable. But really, all of our examples are going to be in L1, which includes measurability. So if you have that, so basically what we need is, first we need a collection of functions that are going to be in L1, and so that's going to be pretty natural for what we're going to be working with. And we need them to converge pointwise to some other function that is going to be measurable for dominated convergence, but we're going to have something stronger than that. We're going to have an L1 function we're converging to, so that's fine. But in order to ensure that this convergence ends up working, we need to get some sort of bounding term. And this bounding term is going to be pretty stupid, but we do need it, and we need it to hold for all x over all m and all x, I should say. Then basically you have this convergence working. Okay, so now what we're trying to do is we're trying to improve continuity, and so in a lot of sense we're going to be leveraging the continuity of something throughout this in order to make it work. And so yeah, let's just keep going up underneath here. So if f is in L1 of R, then f hat is continuous. All right, so put this in the proposition. Okay, so proof. Now if we take a look at it, so we're going to first take omega m to be in R for all m, and suppose that we have Wm or omega m converging to omega in R. All right, so then we need FWM hat to converge to F hat at W. If that works, since this is an arbitrary sequence, that means it's going to be continuous. No, I'm reading the chat. Just kind of focused on writing here. But yeah, I see you there. How's it going? And let's see. It's also my first chat, my first stream, so I'm kind of an amateur with like talking to chat. So anyway, so let's go ahead and write out these definitions, and we can see how this is actually going to end up working. So, so if we take a look at f hat of omega m minus f of omega, we want to get this small. And so this is equal to 1 over square root of 2 pi of the integral of f of x e to the minus I omega m x dx minus 1 over square root of 2 pi integral of f of x. Oh, this should be fm. No, this should be x. Sorry. Yeah. Of e to the minus I omega x dx. Okay, so let's see. Each of those integrals over R, I'm just suppressing that for now. And let's see, I can go ahead and combine some things. So we have f on each one of those. We have an integral. Integrals are linear, so we can go ahead and separate them out. I can factor out that 1 over 2 pi. So we end up getting 1 over square root of 2 pi times the absolute value of f of x, and then I can have these guys, e to the minus I omega mx minus e to the minus I omega x dx. Okay, so is this what I want to be doing? I don't know. Didn't really think this through much before I started. I don't know if I need the absolute values actually for the theorem we're going to end up using. So let's go ahead and clean those up. Boop, boop, boop. Okay, so now what we have is we can start to see what these sequence of functions are that we actually need to work with. So I said with the dominated convergence theorem up here that when we're working with fm, we need a collection of fm inside of L1, and then we need them to be converging to the function that we want. The function that we want to be converging to at this point is going to be 0. And then the sequence fm that we're working with is this entire thing here. And so then I'm going to say that, so basically our fm of x is equal to f of x times e to the minus I omega m x minus e to the minus I omega x. All right, and if I put this in absolute values to find that g, this is going to be less than or equal to the absolute value of f of x times 2. And that's just using the triangle inequality on the second term here. So each of these has norm at most 1, and so this whole thing can't get to be larger than 2. So that's what we get. And then I have this f of x in here. Now, this whole thing is actually in L1 because we assumed that f was in L1 to begin with. And so that means that all of these guys are in L1. Okay, so now we have our sequence of functions that are in L1, and we have a bound on them. That is our g. This is our sort of like, quote, g of x that we're working with here for the dominated convergence theorem. And so we have a bound on each one of them that is uniform. And so, and the function that we're trying to converge to is 0. And so then the reason why this is 0 is because we were saying that Wm is approaching W, and then since E itself is continuous, this goes to 0. So that's going to be vanishing. So then that means that this goes to the integral of 0 dx is equal to 0. So if we take a look at what we just said, is that we have essentially shown that f hat omega m minus f hat of omega converges to 0 as m goes to infinity. And so this is continuity because this sequence was completely arbitrary. So that's pretty nice. Okay. So something I mentioned here while we're looking at it is that in order to get continuity on the Fourier transform, we actually just needed to leverage the continuity of the exponential functions. So basically in here. And that's something that's really common with anything you're going to be doing with the Fourier transform. The Fourier transform more or less is a whole bunch of theorems about the properties of the exponential function. And then they get sort of translated through this integral and multiplication by f. And so that's something we're going to be using a lot. And a lot of times we're going to be using the dominated convergence theorem. We're just going to be using the L1-ness of the function that we're actually working with. So that's pretty good. Any questions? Okay. All right. Well, if you have any questions, feel free to drop them in the chat. I'll try to keep up with it. And yeah, okay, so I was saying before that we wanted to talk about the definition. Boop, we got that. Conditions for it to be well defined, that's good. Continuity for L1, we just did that, and what we needed for that was the dominated convergence theorem. So what's left, I guess, is the Riemann-Lebesgue lemma, which is that got me there a lot faster. What makes a function L1? That's a very good question. So one thing I would say is to be careful about your notation, what you write, because it should be capital L1, because little l1 actually applies for sequences. But for a function to be L1 in terms of being a function, then that is this. Basically, it means that it is absolutely integrable. And so then basically, if you take the integral of the absolute value, then you get something that is finite. You actually spent, if you've taken, yes, exactly, capital 1. Oh, all good. So basically, if you take a look at, say, 1 over, let's take a look at a function, let's say f of x is equal to 0 for the absolute value of x less than 1, and for x being greater than 1, let's make it 1 over x squared. So you get a function that looks like this, and so it's going to be, let's change colors. It's going to be, say, 0 here, and then it goes 1, boop, and it goes 1, boop. This function is actually going to be in L1, and that's because if we take a look at the integral over R of the absolute value of f of x dx, then what we end up getting is we have 0 for that inter term, but then we get 2 times the integral from 1 to infinity of 1 over x squared dx. The absolute value of x squared, but since we're just talking about reals, yeah, it's fine. Absolute value doesn't do anything. And so by the p-test, we have that this is less than infinity. So you can see immediately that if we change this for another function, so if we change it from being 1 over x squared to, say, g of x is going to be, say, 0 for absolute value of x less than 1, but then 1 over x for the absolute value of x greater than 1, greater than or equal to, doesn't matter. Then g is not in L1 of x, of R. And that's just because 1 over x is not absolutely integrable. So that will go to infinity. It's like the harmonic series in a sense, but just an integral form. And so, or rather, I guess you can think of it as just say logarithm. So as we go off to infinity, we're going to basically be getting log of x in the integral, and then as x goes to infinity, the logarithm goes to infinity. So that's what an L1 function is. So an L1 function is a function that is more or less integrable, even in the sense of what you would see in, say, calculus 2. Usually what we work with are going to be Gaussians or Schwartz space functions. And these are functions, Schwartz space functions are just functions that basically decay to zero so fast, or even compactly supported sometimes. So there can be zero outside of some sort of region. And then that guarantee, if they're continuous and zero outside of some compact set or some interval, then you're guaranteed to be integrable because you can integrate over a finite region. And so these are ones that we use a lot, and these are usually called test functions. So that's what we got. And a Gaussian is one example of a test function, but it's not compactly supported. It just goes off to infinity. So, okay. So let's see. All right, so that's the definition. So we have, just to review for everybody's new here, so we're talking about the Fourier transform. And so we have f hat of omega is equal to this integral, which is f of x times e to the minus ixw, or omega. And if this integral makes sense, then we call this the Fourier transform of f at omega. This works if f is an L1 function. And so that's nice. And so if it does work, then the Fourier transform exists for all omega in R. And this really just comes from the fact that when we're using the Lebesgue integral, the absolute integrability implies integrability. So basically we show that this thing is absolutely integrable. So it's integral of the absolute value here. And then basically just by the fact that we already said f was L1, that means that this has to exist. So that's how we get existence. And for continuity, we have the dominated convergence theorem coming in to help us, where basically we are trying to exploit the fact that the exponential function in the definition is actually continuous, and we want to use that limiting property that we get from that sort of continuity of the exponential function. So to do that, what we're going to do is we're going to make up a sequence of functions that depend on that continuity, and then we pass that limit through the integral, and then just say, okay, well, the exponential function is continuous. Once we get the integral all the way through, once we get the limit all the way through the integral, then ta-da, we win. And so that's really what we're trying to do. So what we did here is we took f, and it was inside of L1, and to show that it is continuous, we took a sequence in R, and we assumed that that sequence converged in R. So we have our omega m's converging to omega in R. And then if we have a continuous function, that if we want to show a function is continuous, then we take this arbitrary sequence, throw it inside of our function, and show that the images converge too. So we're sort of showing that the mapping of omega m converges to the mapping of omega. So for the Fourier transform of f, we took their difference, and we expanded them both in terms of the integral. Integrals are linear. That means you can pull them out of the sum, and then that left us with this. And so now we see that the continuity property really just relies on e being continuous. If omega m converges to omega, then this does go to 0 pointwise. And so that's great. And so then we have that pointwise condition that we needed out of our dominated convergence. So this is going to 0. And then we got this sort of dominating term here as just being the absolute value of f times 2. And then that gave us this guarantee of being able to converge here. So I thought that was pretty nice. Anyway, so that gives us continuity. Now we want to prove something a little bit stronger. So this is, we're not only going to have a continuous Fourier transform, but when you have an L1 function, it turns out that you also have a decaying Fourier transform. So it's going to go to 0 as you go off to infinity. This is going to be really important when we talk about short space functions, because we want to show that if you have a rapidly decreasing continuous function, that also maps to a rapidly decreasing continuous function. But that's a lecture for next time. For now, we're just going to show decay. Okay. So let's put a mark down the middle. So what I have in here, cool. All right, so that's our definition of our Fourier transform, so we don't forget it. And so this one is the Riemann-Lebesgue lemma. All right, so basically it says that if f is inside of L1 of R, then the limit as omega goes to, say, plus or minus infinity of f hat of omega is 0. So it says, essentially, if we basically, that, we can have any sort of function, but, whatever our Fourier transform does, it eventually has to decay. And so, but yeah. Okay, so that isn't actually much of a sidebar. That is, so that's actually a really important question. So with L2, you're not necessarily integrable, and the biggest example of that is this g of x here. So g of x, so if you're talking about L2, since we didn't define it, so L2 of R is equal to f going over R to C of the integral of f of x squared dx being less than infinity. So you can have functions that are actually in L2, but are not in L1. And so, for instance, this g of x here, it is in L2, because when you square x, you're going to have 1 over x squared in that integral, and so then that makes this finite. But this is not in L1, so that's where we end up running into some trouble. So essentially, what we need is some sort of sideways method to get to the L2 Fourier transform. And to do that, we're actually going to we're going to show that the Fourier transform of short space functions are taken to short space functions. Short space functions are in L2, and then we'll show the continuity of the Fourier transform with respect to the L2 norm, and then all that together will allow us to get a definition of the Fourier transform on any L2 function through limits. So it'll be a slightly different kind of a definition, but in practice we just write the Fourier transform so people don't get confused, because it'd be really cumbersome to pull out a sequence every single time you want to work with it. So yeah. Is that clear? I don't know. Hey John, so you're asking when people do proofs, are they recalling them from memory or writing them from scratch? How do you approach this? So a little bit of both. So all this stuff I'm showing you is stuff which is basically stuff that is really well known. I've been through this a bunch. I just taught a class. I'm teaching a class where I have this. I just did this week. So a lot of this stuff is just fresh in my head. Some of it though, when I'm like if I'm proving something new, I will often fall back on tools that I've learned over the years. And so for a lot of my papers, I will like hit a problem and I will see if like anything I've done in the past connects to that. And if it does, then that's great. And it comes off, and it might come off as being like off the cuff, like I just brilliantly came up with something, but it was really just pulling from, you know, like years of experience of doing and real analysis and in Hilbert space theory and things like that. And so it's not all magic. It's just mainly a lot of practice. And for this stuff, this is stuff I have to sit down and review, because to be honest, this sort of work is what led to Lawrence Schwartz's like Fields medal. And people worked on this stuff since like I think like Cauchy and Dedekind back in the was it Dedekind? No, Dirichlet. Cauchy and Dirichlet back in the 1800s spent a long time working out all these sort of things, and this is called the Riemann-Lebesgue lemma because you know, basically it was a combination of Riemann's work and Lebesgue's work that led to it. I don't know all the history of this particular lemma, but yeah, that's more or less how proofs end up going. I look them up in a book, and then I try to do my best to interpret them. The Riemann-Lebesgue lemma that I'm going to be giving you here, I literally looked up on Wikipedia and then sort of deconstructed it and put it back together. So I mean, professors even use Wikipedia when they're working. So yeah, and so I actually had a few head scratchers with this proof in particular. So there was something that we end up doing. So it turns out this is really hard to do for L1 functions in general. And so what you need to do is we're going to make two restrictions. And so what we're going to do is we're going to have f be continuous. And I'll show you why we want continuity in a minute. And then we're going to assume that f is what is called compactly supported. Compactly supported. Which basically means f of x is equal to 0 for large enough x. So basically, if once you hit some sort of interval, if you're you're basically 0 outside of some fixed interval, that means you're compactly supported. The compactness basically says that, you know, basically you can fit a compact set around all the non-zero functions values of f. So then so now we have these two conditions, and why are we going to need them? So it's a pretty slick proof here, actually. So I really love this, and so I was really just disappointed actually when I was going through all the results here and scattered data approximation. The book that I use whenever I'm talking about radial basis functions, kernel spaces, and stuff like that, and he has a whole section on the Fourier transform, but I don't think he has anything in here on the Riemann-Lebesgue lemma. And so I think it's a really important lemma, and that's why I looked it up on Wikipedia real quick in order to make sure I could talk about it. And so I was disappointed he doesn't have it in there. He has a lot of really slick proofs in there for like Fourier series and stuff, which we'll talk about when we talk about inversion and stuff like that. But yeah. So here it goes, and it really just exploits the whole periodicity of e to the I theta. So yeah, so basically we're exploiting this sort of periodicity here. And so what we're going to do is we're going to look at f hat of w, and this is 1 over the square root of 2 pi. Integral over r of f of x times e to the minus I xw dx. And what I'm going to do is I'm actually going to shift. So we actually have this integral over all of r. So if I shift r by any amount, it's the same integral. It just means something's going to come a little bit later or whatever, but I mean, it's still all going to be in the integral at the end of the day. So I'm free to move things around a bit and not worry about this change. And so I have the integral over r still, but now I'm going to put f of x plus pi over omega. and this is done e to the minus I x plus pi over omega dx. Okay, so then that's what we got. So omega is fixed, and so that means I can leverage this to do what I'm doing now. And what's really cool is that this is still equal to 1 over square root of 2 pi integral over r of f of x plus pi over omega. And then we have e to the minus I x omega. And then using the exponential property of being able to split terms, we have e to the minus I pi omega dx. So that last term doesn't actually depend on x at all. And so I can actually take it out. And in fact, I don't even have omega in here. Omega canceled. Because the whole point of this was to put omega on the bottom, so it cancels that one there. So now I have e to the minus I pi, which is equal to -1. And so I can go ahead and take that out. And so I have minus 1 over square root of 2 pi times the integral over r of f of x plus pi over omega times e to the minus I x omega dx. Okay, so now here's what the really slick thing is. So now we have this representation of f of the Fourier transform at omega, and I have this one, which also is equal to the Fourier transform of f at omega. And so what I can do is I can go ahead and I can take their average, and since they are the same thing, the average of a number with itself is the same number. So the average of this term with this term is still equal to that. So let's go ahead and do that. And so what we're going to have is we have f hat of omega is equal to 1 over the square root of 2 pi times the integral over r of f of x minus f of x plus pi over omega, and this term times e to the minus I x omega dx. All right, so that's pretty cool. All right, so now let's take a look at what we have. So we have this here, and we're trying to show that as omega goes to infinity, that this goes to 0. Well, if f was continuous, then that means as omega goes to infinity, this term's going to 0, so the inner term's going to x, which means that this whole thing tends to f of x minus f of x, or 0. So we're trying to show that this whole thing goes to 0 as omega goes to infinity. Although we have this problem. F is an L1 function. It's not necessarily continuous. In fact, a slide ago, we just showed an L1 function that had a jump on it. That's not continuous, so that doesn't help us. So what we're going to do is we're going to make the assumption, we're going to assume that f is continuous. Right, so that would help us there. Okay, so now I have a continuous function, and so this sort of helps with limit. All right, so now I'd like to be able to pass the limit as omega goes to infinity through that integral. And but there's a problem. If I want to use the dominated convergence theorem, I need to be able to have a bound on this. And so you'd say, okay, well, last time I just used 2 times f, the norm of f. Maybe here I can take the supremum of f and twice, because I have 2 f's here, right? Maybe that could work. But the problem is that even an L1 function that is continuous doesn't necessarily have to be bounded. And it's one of these sort of really wonky examples, but you could have a function that has a little area here, then you can have a thinner area, and then you could go even higher with a much thinner area, and just keep going. And as long as the areas of all these triangles converge, you can let this get as tall as you like, just the base would change. So that means that you could have continuous L1 functions, so they're perfectly integrable, but they are unbounded, and we don't like that, and that's not going to work for us as far as the dominated convergence theorem goes. So what we're going to do is we're going to assume that f is compactly supported. That is outside of some region, f is 0. So it can do whatever it wants here, but outside of this region it has to be gone. And so what this does is it helps with the bound. For the dominated convergence theorem. Okay, so all right, so then let's go ahead and talk about that then. All right, so now we have a continuous function, that's great, and we have a compactly supported function. We're hoping we'll be able to take this back to all L1 functions, but for now we're just going to live with this, what we have now. And so then what I'm going to do is I'm going to just try to work with what we got. So what you can do is you can have basically we have this compactly supported function. Draw something a little bit easier. Whoop. And so there. And then we're doing some sort of shifting. So this is going to be, say, f of x. And then we're going to have some other function. Shoot. It's going to more or less look exactly the same thing, just shifted a little bit. And so this is going to be f of x plus pi over omega. And so we have these two regions that we're really concerned about. And so, but it's still compact, so we can still get a bound on all that stuff. And so what we're going to do then is I'm going to go ahead and put this other sort of function that we can keep track of everything. So I need to get larger than whatever these guys are. So I'm going to make a function that is basically going to be some constant value up here, and it's going to make sure that I want to make sure I encompass both both of these intervals. Right. So we're going to assume that omega is bigger than pi. It's going off to infinity, so we're free to assume it's as large as we want. And then we're going to have our g of x is going to be equal to the maximum value of f over the interval, wherever that interval is, times 2. And then I'm going to multiply by the indicator function of I plus inflated by say 1. I don't know what, we can come up with this notation ourselves. So I plus 1 basically is, x plus 1 for all x and I, or here, let's say x plus eta for x and I, and eta absolute value less than 1. So basically I'm just saying take this interval, whatever it is, and increase it by 1 in either direction. And that's going to be I plus 1. Just our notation here. Okay, so and then this indicator function of I plus 1 basically is going to be 1 if x is in I plus 1, and it's going to be 0 for x not in I plus 1. Okay, so it's a lot of notation. I'll throw it together real quick. But essentially we're saying that we're just trying to replace, we're trying to get a bound on these guys with some constant function. And that's all this is really saying. And so it's not only up to f, but twice of f, just to make sure we catch the sum of them. And then we have a constant function over as big of an interval as we can squeeze in. Okay, so then this is what we were working with, and so I'm going to copy this Shoo. And we'll move on to the next slide. Cool. All right. And so let me go ahead and erase this. All right, so now we're talking about the dominated convergence theorem, and so basically we're going to be defining some fw. This is a sequence that we want to be converging to the 0 function, and so f sub omega of x is going to be f of x minus f of x plus pi over omega times e to the minus I xw, and we're assuming that it's compactly supported and it is continuous. All of these guys are in L1 because it's really just a linear combination of two L1 functions, which is just f and f again, just shifted. And now we want to show that it goes, and then we can show it goes to 0. So we would take limit as omega goes to infinity, of f sub omega of x is equal to basically f of x minus f, let's see, good way to do this, here. So we can show this limit is 0 by using squeeze theorem. So we're going to have e to the minus I x omega. The reason why I can't show it directly is just because e to the minus I x omega is going to be spinning around a little circle in the complex plane, and so that isn't good for us. So what I'm going to do, though, is that this is the absolute value of this guy, at least, is just equal to this. Boom. And then this goes to 0 as omega goes to infinity, which so then that's really just saying f sub omega of x goes to 0 as omega goes to infinity, and this is for all x in the reals. Okay, so then that gives us our target for convergence. Okay, so all right, so then we have a bound of fw of x for all x is going to be less than or equal to twice of the largest value of x. So I'm just calling this the infinity norm. This is the maximum value of f, and then times chi of I plus 1 of x as we defined, right? So this corresponds to our g of x, or little g. Okay, so then we have that. So we have fw converges pointwise. To 0, which we know is measurable, and in fact is in L1. And we have that fw is bounded by g of x, which is also in L1. Or bounded by g, which is in L1. Okay, so then great. So then we know that we can pass that integral through. Pass the limit through the integral. So thus we have the limit as omega goes to infinity of f hat of omega is equal to the limit as omega goes to infinity of 1 over square root of 2 pi times the integral of f of x minus f of x plus pi over omega e to the minus I omega x dx. And this is equal to 1 over 2 pi times the integral of 0 times e to the minus I omega x dx, or just 0 function. Okay, so there we go. So we've proved this for continuous and compactly supported functions, and then what we want to do is want to take it up to the next step. Now, want to show this for basically f and L1 in general. So there's one thing I can't prove right now. It just may take too much, and we have to get back to definitions of what L1 is and measures and all these other things, which is too much. So what we're going to be using is that for all epsilon greater than 0, there exists a g in L1 that is continuous and compactly supported such that the integral of f of x minus g of x dx is less than epsilon over 3, or epsilon, if we want. You know what? I'm going to need the epsilon over 3, so I'm just going to use that. So epsilon over 3. We can make it as small as we like. And so the intuition here is not too bad. Essentially, you have some sort of function f that is something like this. You know, maybe it has like a few spikes out there or whatever, but you can first cut off the tails at some epsilon, so remove that residue and get rid of it, and then just work with this function here, and then you can get a continuous function that basically gets to be really close to whatever your L1 function is. So even if your L1 function was something like this, we can get a continuous function approximating it that gets really close, and these discontinuities it can keep very, very small with how it chases it. And so we're going to use that the sort of approximation ability of continuous functions inside of L1 in order to wrap this up. And so we have that, and now what we can do is we're going to let omega in R be large enough so that basically g hat of omega is going to be less than epsilon over 3. Okay, so now let's just start taking a look at it. So is that what I want? I think it's fine. So let's see. So we don't have a lot of space here. Sorry, hate skipping over to a different screen, but here. So let's see. So we're going to take a look at the Fourier transform of f at omega, and we want to show that this is going to 0. So this is equal to f hat of omega plus, or say, minus g hat of omega minus plus g hat of omega. There we go. And using the triangle inequality, we are going to end up with this. So this is less than or equal to, say, f hat of omega minus g hat of omega plus the absolute value of g hat of omega. And see, this is equal to 1 over 2 pi square root integral of f of x minus g of x e to the minus I omega x dx, and then this guy is less than epsilon over 3, so I'll put a less than or equal there. Triangle inequality comes in, and this becomes 1 over square root of 2 pi integral of f of x minus g of x dx. So just crashing through the absolute values, and the exponential function just becomes 1, and so we get plus epsilon over 3, and then yeah, so we get this is less than or equal to epsilon over 3 times 1 over square root of 2 pi plus epsilon over 3, etc. And we can make epsilon as small as we like. So f hat of omega converges to 0 as omega goes to infinity. Okay, so that might have gone a little fast. So let's talk about what we just did. So we started off over here, and we wanted to prove something. We wanted to say that if we have an f that is an L1, then the Fourier transform of f goes to 0 as omega goes to infinity, as the frequencies go off to infinity. And so we noted that we would probably need these two concepts, f being continuous. Everybody knows what continuity is, straight out of calculus. F being compactly supported, that is kind of a new concept, but basically it means outside of some interval, it's going to be identically 0. So we're just 0 outside of some region. And so what we did is we took the Fourier transform f, and we came up with two representations for it. We have the definition that we gave here, and then we shifted the whole integral over r to spit out this term, which then becomes -1. So we have two representations of f, this one and this one, and if we take their average, we get this. And I forgot to take the average. Oh my god. So divided by 2, but you get the idea. And so we end up having this, and so then so we end up having this representation of the Fourier transform, and we'd like to say it goes to 0. We can see that if f was continuous, this term goes to 0, which is why we need the continuity. But if we want to pass the limit as w goes to infinity from the outside to the inside here to hit this guy, we need to be able to bound it, and that's because we want to use the dominated convergence theorem. So that's where the compactly supportedness comes from, because a continuous L1 function doesn't have to be bounded. But if a function is compactly supported, then we know that a function takes a maximum value on a compact set. I have a YouTube video on that if you want to go check that out. And so then what we can do is we can take the maximum value that we have on that set, and that's how we end that there. So then that's where we get this maximum, and then on that compact set, we're going to inflate it by 1, so that we can get a bound over that, and also encompassing the shifted and f itself. And so, but once we have all these pieces in place, then we can just pass the limit through and let omega go to infinity, and then this term goes to 0, and the Fourier transform goes to 0 under these two conditions here. So then we just did this kind of formally here, just to make sure that everybody was on the same page. And once we have that, and we have this term going to 0, again, with all the 1/2s that we need, 1/2, then I said, okay, well, we want to do this not only for continuous compactly supported functions, we'd like to do this for all L1 functions. So to do that, what we need to do is we need to take advantage of an approximation ability that we have with compactly supported continuous functions. So basically, anytime we have a function f in L1, then what we're going to have is there's going to be some g that is compactly supported that can get as close as we like. So f is fixed, epsilon, we fix that real quick, and now that epsilon is fixed, we can find this g. and then we can choose this g that is a compactly supported function, continuous function, and then we know we've already established that this Fourier transform has to go to 0 as we go to infinity, so there has to be some omega where this works. So using that omega, we look at this guy here, and what we want to show is that this can also be underneath epsilon, or at least some constant multiple times epsilon, and that'll be sufficient. And so then we use the triangle inequality here. So we took the Fourier transform f and subtracted g and added g. So we added 0. It's a really common trick in analysis if you haven't seen it before. Use triangle inequality to get this, and this term we can show is very small just because when we crash in the absolute values inside of this integral, we get this. And this term here is going to be less than epsilon over 3 times 1 over square root of 2 pi. And then this term came from just the fact that we selected omega to make this Fourier transform small. So that's how we got these terms. So we can show that this guy can be made arbitrarily small for the right selection of omega, and so then that is the theorem. So that's the Riemann-Lebesgue lemma for Fourier transforms of L1 functions. And so we went through quite a lot in these couple hours, and so we went through the definition of a Fourier transform. We talked about the conditions for it to be well defined. Basically, it has to be an L1, and then we come up with new definitions for L2 and distributions and things like that. And then we can show the continuity for these L1, these Fourier transforms of L1 functions, and that leverage dominated convergence. And then we just showed the Riemann-Lebesgue lemma, which says that the Fourier transform of an L1 function goes to 0 as omega goes to infinity. Okay, so what I'm going to do is I'm going to start trying to type this up, and I think I just need to take a quick break, get some water, use the bathroom, and I'll be back. Alright guys, I'm back. So, so I was thinking I could start jumping into Overleaf and start working on the text, but that's maybe not the most exciting thing to see on stream. So I think what I might do is just jump into MATLAB, and so we'll do some MATLAB coding and code this stuff up. I'm going to code the Fourier transform in the dumbest way possible, where I just do it straight from integration using Simpson's rule, and I'm going to show and we have 3 different figures I want to end up making. So I have a figure for L1 functions, basically this figure that I drew for you guys here. So that's going to be something that we can put together. And then I want to talk about have a figure for compactly supported functions. And so that's going to be, something like this. And I want to have a figure for the Fourier transform. So we'll take a Fourier transform of something, probably Gaussian. Let's see. Guys, let me get things rearranged here a little bit. All right, I just installed a new version of MATLAB, so we'll see if this transition works okay. But yeah, let's see. Before I do that, copy that. So this first time doing streaming, so I usually just use this stuff for recording, so we'll see how things go here. Let's go ahead and kill that, and I will paste in iTunes Music. There you go. Cool. All right, so video is not working. Some MATLAB's not coming through right now. Let's go ahead and pull this. There we go. Boop. There you go. Perfect. All right. Looks a little tall. Shrink it down a little bit. And shoot. Okay, cool. Wait a little bit more. Not too much. There. And don't have me in there yet. Where's my handsome picture? All right, let's see. Boom. There we go. Okay, cool. All right. I think the audio is coming through, and yeah. All right, so let's see. It's the first time launching this particular version of MATLAB, so I'm gonna probably have to do some tweaks. That's a good size. Let's see the stream. Yeah, you can read that. Okay, cool. So let's start doing things. So this is. All right, hold on. MathWorks is doing something. All right, so Fourier figures on stream. Okay, so let's start talking about it. So we have 3 things we want to construct. We want to have compactly supported continuous functions. We want to have a Fourier transform. And we want to have a... I have something. What did I say? Was that one? Oh, L1 function. Okay, well, let's see. All right, compactly supported continuous function. That's not too bad. A continuous function is a polynomial, so we can start with that. And so we need to pick some sort of interval. So we'll use. Let's see. All right, so we're going to use polynomial. And let's make it, I don't know, x equals 0 for x, absolute value of x bigger than 1. And I don't know. Start doing that, I guess. So I'm gonna have f of x f is equal to at x, and we're gonna put in here x point, let's try, oh, I don't know, 1 minus x squared. Put a point there so we can put a whole vector in there, and then point times of absolute value of x less than 1. All right, let's see what we get. So I can go ahead and select t to go from minus 5, 0.001 to 5, and we'll just take a look at, we'll say y is equal to f of t. Good, and now let's go ahead and make a figure and plot, we'll say t comma y, and we'll make this blue, I like blue, and then line width, and we'll make that 3. Okay. I'm probably gonna have to leave in about 10 minutes or so, so we probably won't get through all this, but we'll have 1 or 2 figures. Let's see. So if I go ahead and press play, let's see what we get. Change to path, yep. Boop, there we go. So that is a polynomial. That's not very interesting looking though, right? Like, come on, we can do better than that. Let's go ahead and change this to be why'd that cut out? Alright, so let's go ahead and change this to go a little bit wider. Say go up to 3. That seems to be good. And now let's make it so that it turns back around at 3. So multiply by, I don't know, x minus 3, and then we'll say multiply by x plus 2, and then we need it to go back to 3, so x plus 3. All right, so that's gonna be a wonky one. Let's see. Okay, there we go. That's kind of okay, I guess. It's a little big on the right hand side. I know, the art of making figures. I don't like that. I'm gonna multiply it by a Gaussian exponential of 1 of negative x dot squared times this. Let's see. So I'll squish it down pretty quick. Boop. Okay, let's put a minus sign on that. Good. Now let's make it so the Gaussian doesn't crash so fast. Let's see. So I'm going to divide this by 4. There we go. A little sharp at the edge there, but it's still a continuous function, so I think we're good. Okay, I'm happy with that figure, at least provisionally. All right, so, but what I'm gonna do is I'm gonna add on a 0 for whenever we're larger than 3. So, so I'm gonna plot something and gonna do it in red. So hold on, and we'll do plot. We'll say going off to 5. So 3, 5, and we'll put 0, comma 0, and we'll say line. We'll make this red, and line width being 3 as well. Okay, let's see. Boom. Okay, good. And we'll do same for -5 and -3. And that should be good. And let's see, what else? Let's put a little circle in there. And so kind of plot, say 3, 0, red, and let's put a circle. Circle, let's say line width 3. Okay, so that should be good, and we'll put the same one at -3. Right, and so let's go ahead and see what that does. Oh, no, something went wrong. Invalid color marker. Oh, not 0. It's O. Oh, there we go. Let's see. Now press run. We got. Oh, okay. I'm not really happy with that circle though. Let's come up with something better there. But for now, that's fine. So basically showing it's going to be 0 outside of that region when we're larger than the absolute value of 3. And so compactly supported continuous function. Okay. I don't know if that's really convincing or not, but that's what we got. We can come up with an L1 function. And let's see. So we're going to have this being f is equal to 0 for absolute value of x less than 1, and 1 over x squared for absolute value of x bigger than 1. Right, so it's going to be f is equal to at x. We're going to have minus, so 0 is going to take care of itself. So we just need to make sure we turn on when we're outside of this. So we're going to have absolute value of x greater than 1 times, let's see, just 1 over x squared should be good enough. Point divide, because we want to just do all this stuff for each entry in a vector. So now we have t is equal to -5, 0.01 up to 5, and then we're going to have y is equal to f of t here, and yeah, we might have an undefined issue at 0, but we'll see. So let's use this bump, and then let's see. Yeah, we can probably jiggle around this a little bit. If I go choose something that's not going to give me an even multiple, so 0, 1, 3, 2, 1, 2, 3. So we should avoid the 0 there. All right, so let's see. Boom, boom. Don't want this. Just that there. Should be good enough. All right, so let's see for this figure. What do we got? Boom. Okay, yeah, that's not bad. Let's take control of the axes. So axis, gonna say -5 to 5. We're gonna 0 and take it up to 2. I think that should work, unless I'm misremembering how to do that. Yeah, 2 is too much. All right, so say 1.2. Okay. Okay, so I'm not liking the connecting bit there, so we need to get rid of that. What we can do is my headphones ran out of power. I need to get some wired headphones next. But let's go ahead and finish this up, and then I'll just go ahead and take off. So we're going to have f of... I do have wired headphones. Growing pains of becoming a streamer, huh? Yeah, sure. What's the question? Okay, so what is the intended audience? Generally, I'm aiming at engineers, mostly, who want to know more about mathematics. And so I'm trying to make this sort of kind of all-encompassing. It could also be undergraduate students who have, have some experience in mathematics too. So basically beginning graduate students in mathematics, or grad students in engineering, usually control theory, something like that. Generally what I'm aiming for. But I don't know. We'll see where this lands. But I want people to have some experience, basically have some experience with integration theory and things like that. I don't know. If you guys don't think that, if you think it's aiming too high or not high enough, I mean, I'm always open to comments and suggestions. Let's see. There we go. And let's get the music playing again. I don't know. What do you think, Alex? Should I be? Is that too high? Okay, cool. Thank you. Let's see. All right, so we're gonna make t go from so let's say t1 5 to say -1, -5 to -1, and then we can take this to why is nothing coming through my speakers? There we go. There we go. And then let's see, I can take t2 to go from 1 to 0.01 to 5. And we don't need this ridiculousness. And yeah, so then we're gonna have y1 is this, y2 is equal to f of t2, and yeah, so we can plot these in segments. So we have t1, y1, copy that, paste it, t2, y2, there we get that, and then we have plot of -1, -1 to 1, 0 and 0, and red line width 3. Okay. All right, let's see if that looks better. Let's see. All right, so let's run this again. And boom, see what we got. All right, that did not give me what I wanted. Oh, forgot to put hold on. And hold off needs to go up here. Alright, so let's go to this one. Let's run the section. Run section. There you go. No. Section. There we go. Okay, still have those. All right. So you're greater than or equal to 1. Let's see. Let's run the section again. And there we go. And now we just need to put little caps on those endpoints, but I'll do that another time. Okay. All right. So I have other duties to get to, but thank you guys for sticking it here with me for my my first stream. It's exciting, and I'm always happy to answer questions. If you guys want to keep chatting, I have a Discord, and there's a link in the not in the video description, but in the channel about thing, and I'll get more organized about putting it around. But yeah. Join Discord, subscribe if you're not, and we'll keep doing this Fourier transforms and talk about machine learning and stuff like that, aimed at, you know, basically people who have, you know, a good solid understanding of like undergraduate mathematics. And so, and I'll try to explain anything that is even undergraduate mathematics as I can. So, stick here with me, and yeah, well, thank you for watching, and I hope you have a great day.